v minus iw whole square minus, in similar way you will get this as minus norm u minus iw whole square. I will call this as equation number 12. Now again add equation 11 and 12. Okay, then using equation number 8, where is, add equation 11 and 12, then use this equation. Okay, you will get 4 into inner product of u plus v comma w is equal to norm u plus w whole square plus norm v plus w whole square minus norm v minus w whole square minus norm u minus w whole square plus I into norm u plus iw whole square plus norm v plus iw whole square minus norm v minus iw whole square minus norm u minus iw whole square. So this equation you will get if you add equation 11 and 12. Okay, add 11 and 12 and use equation number 8, you will get this equation. Now compare this equation with equation number 7. If you compare these two, you can conclude that 4 into inner product of u plus v comma w is equal to 4 into inner product of u comma w plus v comma w. This is nothing but inner product of u plus v comma w is equal to inner product of u comma w plus inner product of v comma w. This is some arbitrary element, so you can conclude this to inner product of x plus y comma z is equal to inner product of x comma z plus inner product of y comma z. Call this as equation number 13. So equation number 13 is nothing but your property number 3. So we have one more property to prove, that is inner product of alpha x comma y is equal to alpha into inner product of x comma y. So fourth property, inner product of alpha x comma y is equal to alpha into inner product of x comma y, right? So here we will discuss this property for different values of alpha. Say alpha is positive, alpha is negative, if alpha is rational, and alpha is complex. For 4 different cases we will discuss this property. Okay, first property is if alpha is positive integer. So now put x is equal to y in your equation number 13. What you will get? You will get inner product of, I will write in terms of x only. So 2x comma z, which is equal to inner product of x comma z plus inner product of x comma z. This 2 is nothing but your alpha value. So this is nothing but inner product of 2x comma z is equal to 2 into inner product of x comma z. So if alpha is positive, that is some value say 2, your property holds good, right? You can write this to normal general format, that is inner product of 2x comma y is equal to 2 into inner product of x comma y. Now I will prove this result. This result, you can conclude this result is true for alpha is equal to 2. Now I will consider alpha is equal to some n. Okay, let's prove the same result by considering alpha is equal to some n, where n is your positive integer. This is the general case. So what you will get? Inner product of nx comma y is equal to, this is what we have to prove, inner product of n into inner product of x comma y, right? So I can write this as n plus 1 into x, inner product of n plus 1 into x comma y is equal to inner product of nx comma y plus inner product of x comma y using your property number 3. So this is nothing but proving in mathematical induction process. That's how you will do, right? You will first consider some value, you will prove the statement for that, then you will assume that for n it is true, then you will prove for n plus 1, right? In the same way I have considered this. So this is true from property 3. Now inner product of n plus 1 into x comma y is equal to n into inner product of x comma y plus inner product of x comma y. So I will take inner product of x comma y as common. I will get n plus 1. You can write this in this way also, n plus 1 into inner product of x comma y. This is inner product of n plus 1 into x comma y. So the property holds for n plus 1 also. That means this property holds good when alpha is positive integer. Now let's prove the same property when alpha is negative. Okay. So alpha we are considering it as a negative integer. Replace x by minus x in your equation 2. That is your polarization identity. Okay. There you have to replace x by minus x. So if you replace x by minus x here, you will get this equality. So here it is minus x minus y. You can take minus outside. It will become x plus y. So norm minus into x plus y, you can write this as mod minus 1 into norm x plus y. So this value is 1, so you will get norm x plus y whole square. Similarly, I have done the same thing here as well as here. Okay, so you will get this equality. Now compare this equality with this equality. So you can observe here you have x minus y. In equation 2 it is x plus y. So if you compare this thing, you can conclude that 4 into inner product of minus x comma y is equal to minus into 4 into inner product of x comma y. So if you multiply this equation with minus, you will get this equation. Okay. So that is nothing but 4 into minus inner product of x comma y is equal to minus 4 into inner product of x comma y. 4 gets cancelled. You will get this. I will call this as equation number 14. This is for polarization identity. Now I will consider the general case. Say since we are discussing for alpha is negative, I have a negative sign here and I have selected one positive integer. Okay, so alpha is equal to minus beta. If you substitute this, you will get inner product of alpha x comma y is nothing but inner product of, just replace alpha by minus beta. So minus beta x comma y. This is nothing but, since beta is scalar value, minus beta into inner product of x comma y. Minus beta is nothing but alpha. So alpha into inner product of x comma y. These two are equal. That means when alpha is negative integer, your property holds good. Now let's move to rational number when alpha is some rational value. Okay. Alpha is rational means it is in the form of p by q, where p and q are integers and q is not equal to 0, right? So inner product of alpha x comma y become inner product of alpha is p by q into x comma inner product of y. So I can write this as inner product of p into x by q comma y into comma y. Okay. Now if you choose p, just p as a scalar, you can write this as p into inner product of x by q comma y. Call this as equation number 15. Now I will choose one value for x by q. Okay. X by q is equal to z. Then x will become q into z. Right. From this you can write x is equal to q into z. Substitute this here. So you will get inner product of qz comma y is equal to inner product of q into inner product of z comma y. I have written this using a and b, that is when alpha is positive integer and when alpha is negative integer. Okay, using that I have written this. Now you can write this as inner product of x comma y is equal to q into inner product of z comma y, because x is equal to qz, right? Q is some real number. I have taken, since it is scalar, I have taken it outside. Or you can write this as 1 over q into inner product of x comma y is equal to inner product of what is z. Z is nothing but x by q comma y, right? So 1 over q into inner product of x comma y is equal to inner product of x by q into x by q comma y. Substitute this in your equation number 15 here. So you will get inner product of alpha x comma y is equal to p by q into inner product of x comma y. This is nothing but p by q is alpha into x comma y. So you can conclude alpha x, inner product of alpha x comma y is equal to alpha into inner product of x comma y. This is when alpha is complex number, but here it will become, sorry, alpha is rational number, so here alpha is some real number. Okay, so the last case is when alpha is complex number. So complex means we have to replace x by ix in your equation 2. Replace x by ix. So it will become 4 into inner product of ix comma y is equal to norm ix plus y whole square minus norm ix minus y whole square plus I into norm ix plus iy whole square minus I into norm ix minus iy whole square. So you can write this as modulus of I square into norm x minus iy whole square minus modulus I square into norm x plus iy whole square plus I into modulus of I square into norm x plus y whole square minus I into modulus of I square into norm x minus y whole square. I have just simplified this one. Okay, so this is norm x minus iy whole square minus norm x plus iy whole square plus I into norm x plus y whole square minus I into norm x minus iy whole square. This is nothing but, if you compare this with your equation 2, this is nothing but 4 into inner product of x comma y. 4 into inner product of ix comma y. So here it is 4 into inner product of ix comma y is equal to 4I into inner product of x comma y. This is nothing but inner product of ix comma y is equal to I into inner product of x comma y. This is for equation 2. Now I will consider some general case. Alpha is equal to complex means it will be in the form of alpha 1 plus I into alpha 2, where alpha 1 alpha 2 are reals, right? So inner product of alpha x comma y will be equal to inner product of alpha 1 plus I into alpha 2 into x comma y. Now you will get inner product of alpha 1x plus I into alpha 2x comma y. This is nothing but, using your property 3, you can write this as alpha 1x comma y plus inner product of I into alpha 2x comma y. This is nothing but alpha 1 into inner product of x comma y plus I into alpha 2 into inner product of x comma y. Alpha 1 plus I into alpha 2 into inner product of x comma y. This is nothing but my alpha. So alpha into inner product of x comma y. In the LHS side I have inner product of alpha x comma y. So this is equal to alpha into inner product of x comma y. So my fourth property is true even when alpha is complex, right? So from these four properties I can conclude that B is a Hilbert space. So this is all about this problem. Next topic is convex set. Okay, so let's consider a subset. C is a subset of Hilbert space H. I am considering C as a subset of Hilbert space H. If this subset C is called as convex set, it is said to be convex if and only if the line segment joining 2 points of C is also lies in C. Okay, I will consider 2 points, say x and y, which belongs to C. This C is said to be convex set if, so this is my Hilbert space H. C is a subset of H, so I will write this is my C. I will consider 2 points in C. The line segment joining these 2 points should be in C itself. Then you can call C as a convex set. If this is the condition, 2 points are in C but the line joining segment is not in C. You can observe here. This from here to here it is not in C. Then this set is not convex set. But this is convex set. Okay. So that is C is a subset of H. I have considered Hilbert space H and this is my convex, this is some subset C in H. I will call this as convex if and only if the line joining 2 points of C is also lies in C. That is x comma y belongs to C, then alpha x plus 1 minus lambda into y should belongs to C. This is from line joining segment. We are considering line joining segment, right? For that we have used the general form where your lambda will be in between 0 to 1. So if lambda is equal to 2, what this equation become? You will get all x plus y by 2, that should be belongs to C. If lambda is equal to 2, 1 over 2 into x plus 1 minus 1 over 2 into y. So you will get x plus y by 2, that should be in C. Okay. Now let's prove the properties of convex set. First property is a closed sphere is convex. So closed sphere means our set will be in the form of x such that norm x minus x naught is less than or equal to r. This is how our set will be. You have studied in this in first part itself, closed sphere, right? So we have to prove set S is convex. First I will consider some 2 points in S and I will show that line joining of those 2 points is also in S. Okay. Proof. Let x comma y belongs to S. we have to prove line joining segment means lambda x plus 1 minus lambda into y should be in S. This is what we are supposed to prove. To prove this, consider norm lambda x plus 1 minus lambda into y. This is my x minus x naught is equal to, so you can write this as lambda x plus 1 minus lambda into y minus, I will write x naught also in the form of line joining segment. So this I can write as minus into lambda plus 1 minus lambda into x naught. Okay. Lambda into x naught plus 1 minus lambda into x naught. So if you observe this, you will get lambda x naught plus x naught minus lambda x naught. These two gets cancelled. You will get x naught itself. So for my convenience, I have taken in this way. This will be equal to norm into lambda x plus 1 minus lambda into y minus lambda x naught, minus into plus it is minus 1 minus lambda into x naught. So this is nothing but group the terms. I will group these two terms. So lambda x minus, take lambda outside, you will get x minus x naught plus take 1 minus lambda outside, you will get y minus x naught. So if you split these two terms, you will get inequality. So it is lambda into x minus x naught plus norm 1 minus lambda into y minus x naught. Lambda is some scalar value, so I will write it outside. Norm x minus x naught plus 1 minus lambda into norm y minus x naught. Okay, so this is less than or equal to r, right? So less than or equal to lambda into r plus 1 minus lambda into r. Here we have considered for y also. So this, if you consider for point y also, then this will be y minus x naught. Norm y minus x naught is also less than or equal to r. From that I have written r directly. So this whole term is obviously less than or equal to r. You can write it like this, right? Lambda r plus r minus lambda r. Lambda r gets cancelled. You will get r. That means norm lambda x plus norm lambda x plus 1 minus lambda into y minus x naught is less than or equal to r. That means this sphere is nothing but a closed sphere. Therefore, a closed sphere is convex. This whole term is less than or equal to r means this point or in S. This point or in S means closed sphere is convex. Next property is, if M is convex, then we have to prove that M plus x, which is a coset, is convex. If M is convex, we have to prove that coset is also convex. Okay. So given thing is M is convex. That means I will consider 2 points, say M1 and M2, which belongs to M. Okay. So you can write this as lambda M1 plus 1 minus lambda into M2 belongs to M. We have to prove that coset is convex. So I will consider 2 elements, 2 points in my coset. Okay. To prove x plus M1 and x plus M2 belongs to M plus x. That means lambda into x plus M1 plus 1 minus lambda into x plus M2 belongs to m plus x. This is what we are supposed to prove. So I will consider lambda into x plus m1 plus 1 minus lambda into x plus m2. So this will become lambda x plus lambda m1 plus x plus m2 minus lambda x minus lambda m2. So lambda x gets cancelled. You will get lambda m1 plus m2 into 1 minus lambda plus x. So this is nothing but lambda m1 plus 1 minus lambda m2 plus x. You can group these two terms. So this is in m plus x, right? That means m plus x is m plus x coset is convex.